Hi everyone. In this session, we are going to discuss about 2D convolution, part of image filtering. Now, first we'll discuss the concept, then we go for uh, code discussion part, and finally implementation part in OpenCV using Python. So you are with Dr. Divyesh Dibora. Without any delay, let's start the class. Now, as in one-dimensional signals, images can be filtered with various low-pass filters, high-pass filters, and there are so many of them. This low-pass filters helps in removing the noises, blurring the images, while high-pass filters mostly used in finding edges in the images. In OpenCV, we have a function cv.filter2d, okay, and this function is used for this 2D convolution part to convolve a kernel with an image. As an example, we'll try an averaging filter on an image. A 5x5 averaging filter kernel will look like this. Obviously, this image a little bit, anyway, you will understand that this is the kernel. This 1, 1, 1, 1, 1. So in every row, we have these values. There are 5 of them. The operation will look like this, that keep this kernel, this particular kernel above a pixel. At all the 25 pixels below this kernel, take the average and replace the central pixel with a new average value. And this operation is continued for all the pixels of that image. Now you have seen some technical terms here, kernel. So let's first discuss about what is kernel. A kernel is a simple 2D matrix used in convolution or convolution matrix, or a mux used to blur, sharpen, and edge detect in an image. Got it? It is just a 2D matrix. Now, how it works? We all know that images are represented as pixel values in OpenCV, and these pixels are arranged as a matrix to form an image. And we also know that kernel is a simple 2D matrix with specific values in it based on the function of the kernel. Like if the kernel is used for blurring and sharpening the images, they will be different, right? So basically, it is a 2D matrix with the values, and the values may be different for different purposes like blurring, sharpening, edge detection. Okay, now let's take an example. Take an example of this image we are talking about. Here, how many rows are there? 1, 2, 3, right? So first 3 rows and columns like a matrix. We have a kernel of 3 cross 3 by 3 matrix. Each of the pixels in the image has a pixel value, that is pixel intensity. So each of these are nothing but what? Pixel intensity. Now the convolution is done by multiplying the values of each pixel value with the kernel value in the respective places and adding all the values which are just weighted by the kernel by multiplying and forming one pixel. The center pixel, which in this case is 2, 2, and this method is repeated for the rest of the pixels values of matrices in that image. So this is the image, right? So this you can see 3 cross 3. So we are taking this kernel, right? 1 minus 1 minus 1, 1 minus 4, 1 minus 1, 1 minus 1. So respective value, that is t will be multiplied by 1, 4 will be multiplied by minus 1, 7 will be multiplied by what? Minus 1. So each of them, like this one with this, then this one with this. So similarly, 8 will be multiplied by 1, 6 will be multiplied by minus 4, 3 will be multiplied by 1. Similarly, 4 by minus 1, 1 by 1, and 2 by minus 1. So ultimately, we got this one, right? Then all of them will be added, right? You can see here, all of them after multiplication we have added, and similarly we get this value. Well, let me clear the screen. Okay, just a minute. Oh, wow. Now we have specific kernels, 2D convolution matrices to do specific tasks, these things like sharpening, blurring, edge detection. And the kernel here we saw is just an example of, not just an example, not any specific kernel. Means this kernel we have taken randomly, right? And randomly we are taking this, but specifically we have some particular kernels for particular purposes, like identity kernel, edge detection kernel, sharpening kernel, box blurring kernel, Gaussian blurring kernel. Now, like this is an identity kernel. See, 0000100. It is very simple. We are multiplying every pixel value, this adding, and then finding the average value. That is the simple case, right? But the kernel should be specific, like identity kernel. As for edge detection, we are using this -1, -1, -1, -1, 8, -1, -1, -1, -1. For sharpening kernel, this one 0, -1, 0, -1, 5, -1, 0, -1, 0. Then for box blurring, 1/9, all are 1, 1, 1, right? Identity matrix. Then for Gaussian blur kernel, 1/256, then these are the values. So different kernels for different purposes. Then with these kernels, we can form the filtered image by simply convoluting the pixel values of the image and the values in the kernel. Okay, I hope now this concept of kernel is very much clear to you. So for different tasks, we have to take different kernels. Some random kernels by your choice and some specific kernels like these ones I have shown here. Now, if we talk about the current days, current classes function, that is the filter 2D, right? It has the syntax like this: source, destination, depth, and kernel. Source, you got this source image, where filter will be applied on. Destination, name of the output image after applying the filter. Now, this is the very important part: depth, DD depth or D depth, depth of the output image. Now here you'll see that we are giving the value -1, because -1 will give the output image depth as the same as that of the input image. Got it? -1 will give the output image depth as same as the input image. And kernel, the kernel we are taking, kernel, the 2D matrix, we want the image to convolve with. Now, conceptual part is over. Let's come to the implementation, code discussion and implementation part. Code, this is the code. Import numpy as an NP. Import CB to SCB. From matplotlib, importing pyplot as plot. We are importing this pyplot, but as a plot, PLT. Now, this is the source image, IMG. I am taking Lina image as obvious, because we in the last practicals also we are taking the same image. Okay, if image is not found, the message will be like this. And kernel, this is the main important matter. Kernel NP 155 NP float 32 divided by 25. Remember, I have shown you 1/25. All are the 1, 1, 1, 5, 5 cross 5 matrix. Let me come to this part. This one I'm talking about. Okay, this is the kernel I am talking about. So this kernel we have to specify. Okay, I'm specifying in the code. Okay, now let's again come to this portion. So here, this kernel is specified here. NP dot ones, how many ones? 5 cross 5. NP plot 32 divided by 25. Then destination, this filter 2D function is used. Image. So this destination means we are keeping the output image in DST, right? Filter 2D image, input image -1. Depth is same as that of input image. Kernel is this one. Then subplotting, right? Image, original image, x-tick, y-ticks. Then in the second part means one particular image one particular frame is subdivided into 2 subplots, right? One plot is subdivided into 2 subplots. In the second plot, we are showing the averaging or this convolution part, filtered image, right? So plot image show, DST, plot title, averaging, x-tick, y-ticks, plot show. Clear? So code is clear to you now. Let's open the Spider and implement this code. This is the code I have written as it is. I have shown it to you. Just I have discussed each line of the code. Let's run this code. The code is running. See, this is the output. This is the original image. And after this convolution, we got this. This is the averaging image. Okay, this is just an example of 2D filter. I hope it is clear to you, but this classes will be going on. We'll discuss some other filters in the respective classes. Oh, well, that's it for today, but don't skip the practical. The boy is observing you. Okay, bye-bye. Take care.